Welcome everybody. Welcome at part 2 of an event, a session on tool holding. Tool holding, the equipment we use to connect cutting tools to machine tools. Very often overlooked, although very, very important. As always, I'm here together with my colleagues. The four of us, we want to bring today this subject to you in an as lively as possible manner. And by the way, I don't know, some of you hopefully participate next week in the event we have here in Seco, Germany, in Erkrath. Because the four of us will be there, and it would be nice to meet and greet and see each other and discuss a little bit about all those interesting things in machining production. The agenda, as I already said, it's the second part. In the first part, we talked about insert holding technology, because holding an insert in a tool holder is a technology on its own. And we talked about the so-called backends in tool holding equipment. Backends, the part of a tool holding equipment that connects to the machine spindle. Today we are going to focus on the front end of tool holding tools. The front end, the part we use to clamp the cutting tool and connect it as such to the machine spindle. Now, as I said the last time, and it's very important, because if we talk about holding tools, there's quite a lot of norms and standards. And the norms and standards, and we will see today in a couple of cases, that the norm says one thing, but how the norm is filled in by the different producers, suppliers of holding tools, can be slightly different. There can be some interpretation. And I always kind of say it's like if you take the comparison of a car, you have the standard car, the normal car, or normal is perhaps not the correct word here, but let me say the standardized car, and next to that you have a tuned car. Now, in the light of what we talk today, I'm going to focus on standards and norms as much as possible, because the list of things we can do to tune, by means of speaking, is endless. And that is something in a selection process that each and every one of you will need to do, that is take into consideration certain, allow me to say, tuning elements, because they come with a cost. Are they valuable for you? Are they going to give you an advantage that is important for you? Yes or no? But today we focus on the standards, we focus on the norms. And as I already said, tool holding, there are always the two parts. You have the back end, the part which we use to connect the tool to the machine spindle. And some of you perhaps were listening in for part 1 when we talked about it. When we talk about backend, it's the tapers mostly, HSK, SA tape, all those types of things that are important. If you didn't have the opportunity to listen in, you know there is a recording of this available in different media. Today we focus on the front end, the other part of the holding tool, where we connect the milling cutter to, the drill, or whatever cutting tool we want to connect to the machine spindle. And if we look to tool holding in general, what is important? What can we expect from it? What is it supposed to do? There are 3 major elements. One element is it has to position a cutting tool in the correct position compared to the machine spindle and the workpiece. That's one element that deserves attention. The other element is the clamping thing. It has to clamp, it has to fixture the cutting tool in an as good as possible manner to the spindle. And that serves the purpose that it must transmit the possibilities of the machine tool, the accuracy with which the spindle moves, the available power, the torque, the stability, whatever. It has to transmit that as much as possible, because without too many losses to the actual cutting edge. That's the 3 main things we should look at if we evaluate tool holding: positioning, clamping, transmitting. There are some other minor things, although minor, but yet important. The complexity of the system, how user-friendly is it? How easy is it to use? which is, in the light of available expertise around the machine, I talk about the operator here, an ever-growing element today. To which extent is it immune for accidents? Is it safe? Is it secure to use? Of course, that element is to a big extent influenced by the maintenance done and needed. And is what is needed done an important thing? And repeatability. The basic properties, the basic features of the tool holding, we need more than once. Because a tool holding tool is going to be used quite a lot of times. So the features, the original features, how long are they there for us to take advantage of? And how do they behave under load, after load? Because during machining, there are quite some things happening around the cutting edge. There are mechanical effects, thermal effects, and so on. And those things through the cutting edge, through the milling cutter, are ending up in the holding tool. And the question is, to which extent is a holding tool capable of handling those things? There are a million different options when we talk about holding tools. Which one is best? Which one should we select? I always say, when we look to the different principles, let's HSK or SA taper from the back-end perspective. From the front-end perspective, do we use a hydraulic chuck or a shrink-fit chuck or whatever? There are no bad connecting principles. Shrink-fit is okay. And a hydraulic chuck is working well. So there are no bad principles. However, when we look into accuracy and the strength of holding and how the design is done, there are certain tools of lesser quality, of lower price, and that's another aspect. So if we evaluate holding tools from a perspective which one is correct for the application I have at hand, one element is the principle, HSK, HA from a back-end perspective, shrink-fit, hydraulic, power, whatever from a front-end perspective. All principles are good. That's one selection thing. The other thing is, in which condition is it? So, what's the quality? In which, to which extent do you have already experience with certain systems? What budget do you have available if you need to buy certain stuff? Because like everything in life, you have cheap systems and you have not so cheap or more expensive systems. And there's differences there. What do you want to spend? What do you want to get? What's the actual machining process? Is it a machining process that is going to put heavy loads on the tools? Or is it more a finishing type of operation? You need to take that into consideration. And which type of machine do you have? Is it, for instance, a high-speed machine? Is it a machine that uses high RPM? Is it a machine with a monster machine with very high powers? All of those things, of course, influence what you are going to select and use. Now, if we look to front ends, let's focus a little bit more from here on the front end side. And we want to evaluate quality. As I said, you have the principle of clamping. And I repeat myself, but there are no bad principles. Every principle which is used to clamp cutting tools has its advantages, has its shortcomings, disadvantages, and it's a matter of finding the correct solution. But next to it, you have all the other things like accuracy, balance, rigidity, sturdiness, and one very important, and I would like to dive a little bit deeper into that's that so-called runout. Because everybody, when we talk about holding tools, everybody is mentioning the runout is 0.03 of a millimeter over a length of 3 times the diameter. A classic statement. or it's 3 microns, or it's 5 microns. But what exactly is runout? Because it's nice to take that as an element for selection. What's the runout? And it's nice to put forward demands. I want this, I need that. But then we have to know exactly what we are talking about. Now, runout is defined as an inaccuracy in a rotating system. It's if you have a rotating system, look at the picture on top. If you have a rotational stuff that has a rotation axis and you let it rotate around another axis, runout 0 means that the 2 axes fall together. That the axis of the part rotating and the axis around which it is rotating are one. If there is a deviation there, that is what we call runout. Runout is a dynamic thing. And runout, that's a very important thing to realize. Runout cannot be compensated for. If you have a runout of 3 microns, that's it. People sometimes try to connect runout with unbalance of cutting tools. If you have a cutting tool with unbalance can be compensated for. You can take an unbalanced tool and bring it in balance. And runout is not like that. Runout cannot be compensated. It's there and that's what it is. Runout, as such, comes in 2 typical forms. One is what is referred to as radial runout. Radial runout, see the picture on top here again, is when the 2 axes are not aligned, are different, but are parallel to each other. That's referred to as radial runout. Axial runout, and for that see the picture in the bottom here, axial runout is a situation where the 2 axes are potentially falling together, but there is an angle. There is an angular deviation between the 2 axes, and that means that you have the part rotating. It's going to do this. And if you have that phenomenon, that is called axial runout. So if we talk about runout, if we start to have discussions about what is allowed, what is not allowed, we should be very clear. What exactly are we talking about? Radial runout, axial runout, or in case of cutting tools, is it the 2 together that is really important? And if you take a radial runout and an axial runout together, you end up with what is referred to as a total induced runout. And a total induced runout, as the picture, or as I try to show here with the picture, is if you have a reference axis, let's say the spindle of the machine, and to that you have your cutting tool sticking out, and total induced runout is potentially radial runout combined with axial runout, and that means that it's like if you let it rotate and if you follow the surface of the part rotating, everything together, how much is it moving in space? That is what is referred to as the total induced runout. And from a machining perspective, this is what is really important. And this total induced runout is partly a given thing. It comes with the quality of the tool holding and the machine tool and the cutting tool. But to a big extent, it's also influenced by how the whole thing is handled by the operator or by the tool setter. It refers to quality of manipulation, I sometimes call it. How, to which extent is the one working with this knowing what he or she is doing when clamping cutting tools? That's the TIR, total induced runout. And I try to give you here a feeling for what it means. What you see to the right here is a milling cutter turning around with a runout, total induced of 0. The axis of rotation is the axis of the milling cutter, and angular, the two axes are aligned, there is no deviation. What I try to simulate here to the left is a milling cutter which has a combined radial and axial runout. And you see how the milling cutter is moving then. And I draw the nominal circle, the blue circle. Around that I have been drawing a red circle. That is the circle in which the tool is rotating around. And if you try to follow a little bit the picture to the left, what you see here is that you have here an operation where certain cutting edges at certain moments in time will be overloaded. The feed will be quite a lot higher than the feed which you programmed, which you thought you were using. On the other hand, some other cutting edges will be undercutting, not cutting perhaps. And this will lead to a total random behavior of a milling cutter. If you have such a situation and you want to make statements, you want to do things with estimated tool life and all that type of stuff, well, good luck, because you have an issue. So runout, axial runout, radial runout, total induced runout is quite an important thing if we talk about tool holding. And if we have runout issues, as I said, it cannot be compensated. It's not that you can adjust something to take it away. You have it or you don't have it. And if you have it and you don't want to have it, you have to evaluate where the real cause of it is. And the cause of runout can be bad contacts. Bad contacts between the spindle and the back end of the holding tool, bad contacts between the front end and the milling cutter. And anyway, there's something wrong in how you assembled everything. That can be a potential reason. This has to do with the condition in which all the elements are. This has to do with respecting certain rules on how to do certain things and so on. It can be that you didn't respect, how should I say, clamping instructions. Because, the old-fashioned mechanical stuff, the more is better. You know, if you have a key with this length and you are supposed to use that, the average operator doesn't trust that, put a tube on it and do some extra. That type of stuff will lead to potentially run out. Good maintenance, cleanness of everything can be a reason. The initial quality, let's call the animal an animal. Low quality tooling, cheap tooling. There are consequences with that. Unbalance, centrifugal forces, cutting forces can lead to certain things, and long tools. Because if I go back to my axial runout, you know there is an angle between the two axes. If there is an angle between the rotational axis and the cutting tool, the longer the tool is, the bigger the deviation will become. So the tool overhang, the length of the tool, plays also an important role here. And that brings me to some conclusions. Runout. A very important thing. People talk about it, people have demands about it, but I have a feeling based on my own experience that people not always fully understand what runout truly means. And also, I sometimes have a feeling, in part one, some of you perhaps remember that I was talking about the multiplication effect. If you have things which are no good. Because runout, it's good to say, like in the example you see here, I allow maximum a total induced runout of 3 microns, but the big question is over which length? A short tool or a long tool? Makes a big difference. So if you want to evaluate the quality of certain tool holders, evaluate the quality of the long tool holders, I would say. And if that is good, trust me, short normally also will be good. Don't do the inverse. Low runout only gives you advantages. The operation is safer. You remember the milling cutter doing all this type of stuff. Unbalanced, broken cutting edges, excessive wear, irregular behavior of the tool. So the operation is much safer. Tool life will be a lot longer. That's what I tried to show in the little diagram to the left there. How tool life is influenced by runout. And this is no theory, this is empirical. You can measure those things. Better surface roughnesses of the machine surface, obviously, is a big advantage. And perhaps some of you say, not so important, but anyway, if you are standing the whole day next to a machine tool, it's an important element. Lower machining noise levels during machining. Length of the tool came a couple of times around the corner here. There's something in tooling which we refer to as tool slenderness. Tool slenderness is the length of the tool out of the reference line, the gauge line of the tool holding thing. And that length, very often we work with a ratio factor called the slenderness, which is the length of the tool measured with the diameter on the gauge line. And that's called the slenderness, length divided by diameter. If you dive into the theory of all this, you learn that length, the longer the tool, if you take a double length as a practical example, the risk for vibrations will be 8 times bigger, not 2 times bigger, 8 times. We are not going to dive into the theory. I hope you trust me a little bit on this. But the double length is 8 times more risk for vibrations. I don't say it will vibrate, but the risk will be higher. If you have a double diameter, you will have 16 times less risk for vibrations. So the impact for diameter is double the impact of the length. That's why we always say good practice in tooling is short and as sturdy, as big as possible is always the best choice. But in some situations, see the photo I show here behind me, we need long tools to fulfill the needs of the application. If you have to do things along steep walls, you need a long tool. The tool holding material. Is an important element here. It's about Young's modulus of the tool material. The stiffer the material, the higher the Young's modulus of the material, the less bending the tool will have, and that increases the resistance against vibrations. And there are some guidelines. Normally we say if the length of the tool is less than 3 times the reference diameter on the gauge line, normally you don't have vibrations, you don't have to worry. If it's bigger than 3, below 6, there is a risk for vibrations, you better be careful. If it's more than 9, you'll have vibrations, but they will be controllable. And while making this statement, I see here a typing error on the slide. It says less than 9. More than 9, you have for sure vibrations. If you have a length of a tool which is more than 9 times the diameter at the gauge line, you need to take preventative measurement if you want to avoid standstill, because you have to solve vibrations. Now, if you look to that so-called anti-vibration tooling, then you have I'm always a bit careful with what word I should use, but you can try to avoid problems with vibrations and run out and stuff in an easier way with more traditional tools by using elements like stability increase due to tapering. If you have a cylinder and if you make it a taper, per degree taper angle, the stability goes up around 8 to 9%. So if you need really long tools, but you have the possibility to use a tapered shank, that's better. That will give you a more stable setting. That's why some people always ask that question. They say, why do you have so many different shapes and lengths and stuff like for all these holding tools? But that's the reason. If that doesn't solve, of course, you can start using anti-vibration tooling. Anti-vibration tooling, you have very difficult systems, you have rather easy systems. What I show you here is what is most probably the easiest system available on the market. It's a principle where a vibration is balanced by a counter vibration, and you see it here in the video where we try to simulate it. To the left you have a free balancing or a free moving structure, and to the right you have a structure which is kind of compensated by an internal thing that damps the vibration. And you can see for yourself what is happening. If you allow that thing which is built inside to damp the vibration, what is happening now, this is the result. This is what is called anti-vibration tooling, which is also a possibility for longer tools. Front ends, you have the traditional front ends. I can go quick, I suppose, here. For each, I have a description. The standard norm, as I say, you have the norm and then you have all the differences on the norm. But the norm is, there is one ISO norm. This is a typical holder we use for face milling cutters, square shoulder, the bigger square shoulder milling cutters. You have also the system, the shell mill system for the really big milling cutters with the screws and the tenon drives. You have a combination of those two, which is called a combi shell holder. Also here there are some norms defining that. What you see is for each of these things is given according to the norm what should be the maximum allowed runout. If supplier by supplier this demand is met is another story, but at least this is what is put forward in the norm. Disc milling cutters, especially what is called the A-type disc milling cutters. They are specific holding tools for that type of milling cutters. It's called disc mill holders. Not so much to say about this. You have holders for drills, the universal drill holders. You have, it's still used, but not so much anymore. I think here mainly for the bigger high-speed steel drills. There are still some where we use drills with Morse holders. This is kind of a connection. Tapping holders, driven and free. Are a family of holders for tapping tools. All of these I refer to as the rather standard holders. Then you have the holders for end mills. Now, if we talk about holders for end mills, we first have to talk a few words about the shanks of end mills. There are basically 4 different shank types for end mills defined according to the norms. You have cylindrical, you have Morse taper. I think this one is nearly disappeared when it's about milling cutters. We find it, as I said, on some of the high-speed steel, the bigger drills still, but anyway, it's still part of kind of standard thinking. You have the Weldon and the whistle notch shanks. You know, that's the cylindrical thing with the flat or 2 flats defined depending on the diameter. And you have whistle notch with face. These are standardized, at least, the 4 basic shank types for end mills. And each time when I see this picture, I wonder, do some of you know why, if you look to these milling cutters, there's somewhere a part of the shank which is always a little bit, the diameter a little bit smaller? At least in the past it was like that. We find it lesser and lesser today, but in the past we had that. Does anybody know why that is? It's not just for the beauty, eh? People think, oh, it looks good, but there is a technical reason for that. But if some of you perhaps put it in comments, I'm really interested to hear if people still possess this a little bit old knowledge. Holders for shank-type tools, end mills, some drills. If we look to these, there are a number of principles we used. Which principle is most appropriate is depending on a number of things. What are the dimensions of the tool you want to clamp? What is the type of tool? What type of shank do you have? If you have an end mill with a cylindrical shank, yeah, you need a holding tool that can clamp cylindrical shanks. Yeah, easy. It's also depending on the type of application you have. Which milling strategy are you going to use? Is it high RPMs or is it high depths of cut? What type of loads are going to act on the milling cutter? What cutting conditions are you thinking about? What's the length of the tool? All of those things will influence which type of clamping you use. But anyway, principles are well done. Well-done clamping is a way of clamping where I have a tool with a cylindrical shank with a flat on it, or two flats depending on the diameter of the tool. The bigger diameters have two flats. And you put that in a well-done holder, and on the flats you have a screw clamping the tool. That's well-done. Rather straightforward, simple clamping system. Well-known. Most people are familiar with it. The main advantage here is it's strong. Before you move the tool in the holder, trust me, you crash the machine tool. On the other hand, seeing the type of clamping we have here, by definition, you are going to have radial runout. You push the tool to one side, so you will have runout, you will have unbalance. And that means that there are limitations to what you can do with this type of clamping. I mean mainly applications where we talk about high quality or high RPM. Whistle notch is very comparable with Weldon, but the screw clamping on the two flats is not going to clamp perpendicular to the shank, but under a slight angle. As such, when you clamp, you pull in the tool into the holding tool. In the holding tool you have a screw which mostly is adjustable. That means that you have kind of a reference, and if you change tools in this holding system, you will have the length of the tool will always be fixed, which is something you don't have with traditional Weldon. There, after each time you change a tool, you have to measure the length of a tool again and change, if needed, the settings in the machine. With whistle notch, you don't have that system. Whistle notch with flange is the same system, but here it's comparable. You remember when we talked about the backends, we said you have the SA taper and you have SA taper with flange. If you have such a system, you have a double clamping. You clamp radial and also axial. You pull the flange against the holding tool, and as such you create a much stronger clamping. That is referred to as the whistle notch with flange. It's even more accurate as traditional whistle notch, and it's more stable. The clamping creates a situation which is a lot stronger. Collet chucks could be one of the oldest clamping systems. Collet chucks is a holding principle we use for tools with a cylindrical shank, basically. It's a very simple thing. You have an expandable or reducible collet. You put it around the shank, and in clamping, you clamp the tool in the collet. That's the principle here. Over time, quite a lot of types of collets have been designed for collet chucks. Some of these collet types could be defined as very strong. Others can be defined as very precise. Others can be defined as rather simple, maintenance-free, nearly. Nothing is maintenance-free, but anyway. So that is, I would say, a fast overview of what I refer to as the traditional holding tools. As I said, each and every one I showed as a clamping principle is okay. Which one is most appropriate for your application is depending on the application, on the loads, all those type of stuff. Principle is one thing. How the principle leads to a tool assembly, a milling cutter in a holding tool in the spindle, is not just the quality as such, but is also depending on the quality of manipulation. How good are the people working with this, knowing what they are doing, should do, and do they actually do it? Front ends. I remember somewhere in the 90s we saw the birth of machines with higher RPM, and suddenly, from a tool holding perspective, we were confronted with different needs. We saw a different type of tooling appearing more and more, what we refer to today as solid carbide tools. End mills in solid carbide, not in high-speed steel as before, or the so-called insert system type end mills, but solid carbide came into use. Machine tools were different, the RPMs were higher, the type of applications were different from before. We saw the birth of longer and longer tools, so stability became an issue. And in those new situations, when people evaluated holding tools, 4 of them came forward as more appropriate for this new situation. I nearly was going to say new generation, but that's perhaps a too big word. And what we see in today's world, what was revolutionary, new in the 90s, today became daily routine, is hydraulic chucks, shrink fig holders, power chucks, and high precision collet chucks, as quite often used when it's about end mill type or shank type tool clamping. Quality here focuses on the things which are really important when higher precision is needed, when higher RPM is being used. It's about balance, run out, precision, rigidity, and that type of stuff. And if we look to this, first of all, we have to realize about the variables we are confronted with. And I focus here on transmittable torque. To which extent the torque of the machine tool are we capable of putting it on the cutting edge? To which extent is the holding tool going to transmit the torque from the machine tool on the cutting edge? And people, they too often think that black and white. It does or it doesn't. Now, it's not like that. It's a more analog thing. And what you see here, for instance, is transmittable torque depending on the shank diameter. The horizontal axis is different shank diameters. The vertical axis is transmittable torque. You see 2 lines, one with low RPM, 0, static situation, one with a higher RPM. And what we see is that the bigger the diameter of the milling cutter we clamp, the more torque we can transmit. Obviously, that's mechanics. The example here, I have to mention this is for shrink fit clamping, because the type of clamping principle, of course, plays a role in here. What you see here is the impact of tolerances of the tool, the tool shank, what are the tolerances you have on the tool shank. And here you see a situation that, and again it's an example for shrink fit, that the better the tolerances, the lower the tolerances on the tool shank are, the better the clamping is in case of shrink fit, and that means better clamping is more transmittable torque. So I need a tool with a high quality shank becomes very, very visible if you see this graph. It's not just by means of speaking. And the last thing I want to draw your attention on is the RPM. Because the higher the RPM, all tool holding have a tendency, if the RPM increases, that the thing expands. And expanding means losing clamping force. And if you lose clamping force, the transmittable torque is going down. What you see here on the vertical axis is the widening that happens under influence of RPM. And if the thing is widening, you lose grip. And if you lose grip, you lose the ability to transmit torque. So what is the RPM? What is the dimension of the tool? What is the quality of that shank? It's all very, very visible if you start to have this type of discussions. Hydraulic shocks. I think most people are familiar with how a hydraulic shock works. I don't want to spend too much time on it. It's one of the things we use today a lot. Advantages, I would say it's good clamping, very good run out. Theoretically, if you have a tool with a good quality, and if you have a hydraulic shock with a good quality, theoretically your run out will be zero. But okay, zero is a very, very small value. From a balance perspective, rather good. Disadvantages, I would say it needs maintenance, and people forget that now and then. It's a bit of a costly system. And if you have radial mechanical loads, it's sensible for that. So I would say I don't say it can't stand radial loads, but you should be a bit careful with it. Power chuck. A power chuck is basically trying to do the same thing as a hydraulic chuck, but here we don't use hydraulic force to make the clamping, but kind of workpiece deformation, material deformation. And by if you have a hole which is not round and you put something round in it and you deform, you have kind of a clamping. And that's what we do with power chucks. Power chucks are strong, rather rigid, not so expensive, but run out is less. So I would say in situations where precision is your main concern, perhaps be careful with power chucks. Shrink fit. I like personally shrink fit most. I think it's a very, very beautiful system. It's accurate. It's easy. It's simple. It's relatively maintenance. Simple. I don't say it doesn't ask for maintenance, but it's a rather simple system. It's very accurate. This is perhaps the youngest clamping system, and I would say there are still some things where we are working on, and we is all the suppliers of holding tools, because the DIN norm for shrink fit determines how much torque must be transmitted for certain type of cutters in certain diameters and so on. How that is made possible is still subject of research. So in shrink fit you have still a bit of research going on. Advantages, as I say, I see quite a lot of advantages. The The disadvantages for me are that the quality of the tools and the quality of the shrink fit holding is important. Could be the most important thing to make this work. So if you have lower quality tools in use, I would say be very careful with shrink fit. Shrink fit also, you need extra equipment. You need equipment to make the shrink fit clamping happening. And the equipment is one thing, but having operators that are trained and educated on how to use the equipment, that's perhaps the bottleneck of this system. That's perhaps where we have now and then issue. I can say out of personal experience, 95% of issues with shrink fit, that the thing does not deliver what was expected, can be brought back to bad manipulation during clamping or unclamping. That's the reality. That's shrink fit. Collar chucks, also collar chucks are used for higher precision, for higher RPM, but then with the so-called HP collets, the collets that gives us high accuracy, high strength. I think this is perhaps the most flexible system, flexible in such a way that if you think shrink fit, if you think hydraulic to some extent, a little bit more flexible. But anyway, one holder clamps one diameter of shank. That's a bit the principle. In case of collet chucks, of course, you can have one holder, you can have different types of collets, and depending on, types of collets, dimensions of collets, and depending on the dimension of the collets, you can clamp different diameters of milling cutters in one holder. Although, personally, I have doubts in the present world if that is still a need for holding tools. But that's another discussion. Runout should be checked on a regular basis, and potentially unbalance also should be checked on a regular basis with this type of thing. To end this session, a few words on modular tool holding. What do we call modular? Modular is a type of tooling where in between back end and front end, we use extensions, reductions to create specific longer or bigger tools. That is what is referred to as modular tooling. Where do we use modular tooling? Well, that is depending on the batch sizes. Big batch, small batch. The smaller the batch sizes, the more people could consider modular tooling. If you have smaller batches and if you do the smaller batches on different types of machines, I mean, today you do it on this machine, tomorrow you do it on another machine, it could be interesting to take into consideration the options, the possibilities of modular tooling. Instead of the so-called solid tooling, solid is where modular and where back-end and front-end are one part. Modular tooling, yeah, the advantage in one word, it's modular. You can build kind of your own tool depending on the application you have at hand. The tool which fulfills the most your expectations. That advantage is also the drawback. You need somebody who can do this building together. Again, it goes to the expertise of the operator. Using modular tools, yes, but you need knowledge. Modular tools gives you the possibility to handle long tools. You remember when we talked about the length of the tool slenderness, as long as it's slower than three times the diameter at the gauge line, you are safe, no problem. But when tools are getting longer, you end up in a situation where it could be risky. When tools are getting really long, you end up in a dangerous zone, the red zone. But that red zone you could compensate by using intermediates in your modular tools with reductions, with tapers, with angles to bring a bad situation into, I would not say a good situation, but an acceptable situation. Summary, as far as we can talk about a summary, let me focus on the things where we have most discussions, because shell mill holders and that type of thing, it's a rather straightforward thing. But if we talk about holding equipment for end mills, for tools with a shank, being it solid carbide, being it in some cases high-speed steel, being it tools, insert system tools, but anyway, shank-type tools, end mills. And if I take those tools in the present situation directly, the present situation of higher RPM, high precision, longer tools, unstable tools, I think there are three types of clamping from a front-end perspective that deserves our attention. Call it hydraulics and shrink fit. If I compare the systems very, very shortly, you remember I talked a lot about runout. Runout, I think, is a very important thing. If we look from a runout quality perspective, shrink fit is the best. Hydraulic is somewhere in the middle. Collet is, I'm not going to say bad, but the least of the three. Another important aspect is strength. How good is the clamping? How much torque can be transmitted without losing stuff? Collet is okay. Hydraulic is a bit less. Shrink fit again is best. But I talk here with some precaution, with some care. Everything also depends on the, as I referred it a couple of times now already, quality of manipulation. It's not just the inherent quality of the tool, it's also how the tools are handled. Relative cost. If again I take my collet as a reference, hydraulic is a bit more expensive. Shrink fit has the lowest cost. A remark on the side, of course, shrink fit, you need extra equipment. You need a shrink fit device to make the shrinking and unshrinking of the tools. A little bit more complex or complete, which is most probably not readable for you, but don't worry, as always, if you want to have a copy of this presentation or this table here you see behind me, leave me your email address or leave me in the comments somehow that I know how to contact you, and I forward you the presentation, this table, and whatever more information you would like to have. But what you see here is the basic clamping principles for end mills, as I said, shrink fit, collets, power, hydraulics, and side lock. Well done. Type of operation, where is it advised for, where is it applicable, where should you stay away from it, and then the features, the characteristics, what you can expect from it. And selecting is kind of using an overview like this, and it's a bit of yes-no. Describe what you want to do and find a system which suits you best in that application. Of course, remember what I said in the beginning, next to that you have to take into consideration also perhaps already existing systems in your workshop, your own preferences, your own experience you have with clamping systems and so on. But it can serve as a guideline, an overview like this. Which brings me a bit over time, but anyway. If, you know, we have quite a lot of literature on machining applications or machining as a process. If you want to have more information of that also, please let me know. And we can make sure you have all the information you want. I don't know, let me check if while I was talking there were questions coming in. I see not so much, but anyway. I see quite a lot of questions on runout. There was also a question, what are key considerations for selecting a type of tooling? See the last overview I showed you, that can help you. What is Young's modulus? the Young's modulus, also called modulus of elasticity. That's a mechanical figure that indicates the stiffness of a certain material. To which extent is a material, when you try to bend it, what I'm saying now is not exactly correct, but anyway, if you try to bend it, to which extent is it going to resist that? To which extent is the material stiff, unbendable? That is Young's modulus. Can total induced runout be compensated for? No. It's there, and if it's too much, you have to find other ways. How is minimizing runout in machining processes going to contribute to quality and efficiency? Yeah, that's something we talked about, and I hope the couple of minutes we spent to it, that I gave you already an answer to that question. If a tool is rotating really without runout, both axial and radial, you have the tool in the position where you expected it, and a position to which you contribute certain results of the operation. So, and the results is quality of the machine service, vibration-free machining, predictable tool life, rational wear patterns on the cutting edges, and so on. One last question. Are you sure about your definition of axial runout? Yes, I am. And I know that's quite a discussion in the mechanical world, because if you talk about axial runout, if you Google it, or if you use artificial intelligence and you ask the question, what is axial runout, you will have two answers. One answer is that if you have something, rotating part, axial runout is defined as a potential movement like this. That kind of, let me say, the tool moves in and out. Some sources refer to this as axial runout. But how should I say, the scientific definition, also the definition in tool norms and standards of axial runout is, as I presented it here, it's you have the rotational axis, you have the axis of your tool, and if the axis of your tool is under a certain angle compared to the rotational axis, the axis of your machine spindle, that is what this angular deviation is what is referred to as the axial runout. I see the time is up. There are some questions. There is no time to answer, but I answer the questions in the comment afterwards. If you have more questions, please put it in comment or send me a mail, and I try to answer as many as possible of the questions you have. As I already said, if you have, if you want to have a copy of this presentation, if you want to have the overview I showed on one of the last slides, or whatever extra information you would like to have, just let us know, and we try to send it to you. As I said, I hope some of you perhaps we can meet next week when we have here in Seco, Germany, the Automotive and General Engineering ITI days. Everybody is most welcome if you haven't registered yet, and you are free those 2 days, or perhaps you are not free, but you are really interesting to learn about what's going on in the machining world, in the industry segments, general engineering and of automotive. Please register, most welcome. We hope to see you there. We hope to meet you there, have a coffee together and discuss a little bit. And next month, I want to invite you for the next event, 26th of March, where I want to dive into, machining by definition is intuition driven. The experience of the operator, he has it in his fingers. The future is data-driven, algorithm-driven, the so-called digital machining, as some people call it. Now, in between intuition and data-driven, you need models. So based on the data, you can create your algorithms. And that's the subject for next session. Model-driven machining. What are the models we can or we should use to define a machining process? So all the data we have around machining processes, we can use to create algorithms. Algorithms we can use to improve machining processes, to optimize machining processes. But that's for next week. Next month. I hope to see you there. I hope today, together with the previous session, because it was a part 1 and a part 2, give you a bit of a insight in tool holding. As I said 2 or 3 times now already, tool holding, it's always a bit forgotten, and that's not just. Tool holding is important. You can have the best machine tool in the world, you can have the best cutting tool in the world. If you are unable to connect the two together in the best possible way, well, tool holding, which is a link, will be a missing link then. And that missing link will determine your real productivity, whatever tool or machine tool you use then. Thank you very much. Looking forward to meet you again, or next week live here in Seco, Germany, or next month virtual here again in the GT events. Thank you on behalf of my colleagues.